Let's begin. Welcome back. I hope you're having a good first week. I'm still here, and whoever is tracking my progress throughout the semester, I'd like to see the statistics by the end. So I walked without my walking stick last time, but I'm still going to use it because I like it. It's a good pointing tool. I want to finish off. There were two more slides we didn't cover last time. I will finish those, and we'll get started on statistics. We will start easy, as you will see. But I want to give you some homework thoughts as you work through your homework. And I give these in all my courses, because all my courses involve some level of computing and programming. So you see the words programming, although not every assignment you're going to have to do programming in it, at least not at the level of numerical methods. But there will be an opportunity here and there. So getting an answer is not the goal in homework, is rather critically thinking about what the answer means and whether the answer makes sense or not. I'll give you an anecdote. So I am a human being, like you are, as all your teachers are. I remember when I was doing my bachelor's, about 2 years ago, I was doing my bachelor's and in mechanical engineering, and I had an exam in heat transfer. And the exam was on radiative heat transfer, which normally isn't necessarily covered in chemical engineering in the past, but it's a tough pill to swallow, radiative heat transfer. And the question was, consider two spherical heated balls in outer space, and each one of them was at a temperature of 1000, and find the temperature in the middle. And I ran the calculation, and I remember that day I had a terrible headache because I'm a human like all of you are, and I had the jitters, and it was on the final, and that was probably 30%, 35% of the entire exam. And the temperature in the middle, I ended up getting 10,000 kelvins. I'm like, this just doesn't make sense. So at the bottom, I wrote to the professor, this does not make sense. I must have made a mistake somewhere. That's it. He gave me full credit because I had the mistake was in one of the constants, the Boltzmann constant, and so it was like 10 to the minus 17. I put it at like 10 to the minus 10, some small error, right? And so if I had stopped at 10,000 and said the temperature halfway between the two heated spheres was 10,000 kelvins and stopped there, I would have lost all credit. But it's the interpretation that, okay, this didn't make sense. And if I had more time, if this was not a timed test, if this was a project, I would have said, this doesn't make sense. Let's, take another look at this. So getting the answer is not the goal. And sometimes you will stop before even you get to the answer. But it's about the methodology, about the pseudocode, about the algorithm, if you want, the steps you need to get to the answer, because the steps are the harder part. Doing calculations is easy, right? You can get a calculator and do calculations, make a mistake or not. And for those who work with me, they often know I'm like, it's an algebraic calculation. I don't care about that because any calculator can do that, right? But it's thinking about the problem and dissecting it. That's more important, critically thinking about it. And I guarantee you, if we have a written exam and you get an answer and you tell me, this doesn't make sense, I will look very, very, very favorably at that because that's what I'm looking for. If we have to write code, writing the code is not the goal, and I hope you learned that in numerical methods as well. You are not here to write code. You are not here to do computer science or programming. I know many of you love programming. I love programming. I almost quit engineering because of how much I love programming, and I used to be like the only kid on the block who liked programming, and everybody else, thought I was like such a weird nerd. Like who's talking now, right? I mean, coding is like one of the most important things you can do, but it's going to be obsolete at some point because AI is going to do it all for you. But what's more important is figuring out what you need the code to do, right? The programming is just a language, just like any language you speak. Spanish, English, Chinese, Arabic, French. But the idea is more important than the programming, because the idea transcends the programming. The programming is just a language to communicate with the computer, right? So you can express any idea in different languages, but it's the idea that matters, okay? So focus on the idea, what you need to do. And finally, how you present your results is often as important as the results themselves. We spend, in my research, we do a lot of computing, we deal with a ton of data to visualize, and sometimes we would spend, say we spent 3 months on running the analysis to get the data and do the simulations. We would spend 6 months on just 4 or 5 plots or figures just to present the data in the best possible, cleanest, most concise way. All right, so the way you present your data is more important than the results, frankly, because you could have great results but totally screw up and present the data in a terrible way, right? I was talking to, I'm sitting on a few school boards, and yesterday we had a school board meeting. It's a little private Catholic school, and they were having like an open house night, and like tuition, let's say it's $8,000 a year, and like they're going to say, oh, tuition is $8,000 a year. I was like, no, maybe present it in a different way. Maybe say, for the same cost of daycare, you could put your kid in a private Catholic school, or for $10 for the cost of 2 cups of coffee, right? $10 a day, you can put your kid in a good school, right? So different ways of presenting the results. You're not lying about the results. Be very careful. I'm not saying that. You have to present the results in the best possible light. Now, with statistics, as we will see, you can cherry pick and do lie a lot while telling the truth, because you're picking from the data itself, right? So you're picking from the facts, but you're cherry picking, and you can sway opinion. Now, in terms of how we are going to use calculators to do statistics, should we do Python? Should we do Excel? I still wake up at night asking myself this question. Are we going to switch entirely to Python? Are we going to be doing it in spreadsheets, or stick with Python, or both? I don't have the answer, because I want you to learn statistics first before you learn how to compute statistical things, right? So that's more important to me. And if Python and fancy coding in Python is going to stand in the way, and it will, because there's a lot of libraries and hoops and loops we have to go through just to get to a simple answer, that defeats the point of learning statistics. So the methodology, the idea is to use the right tool for the job. And as you will see early on in the vast majority of problems, we just have to calculate a certain probability to make an inference. And you can do that with a simple line in a spreadsheet and move on with life. If you were to do the same in a Python notebook or Python code, it will take you probably 20 lines just to get that same answer. And every time you have to change the numbers, you have to re-execute and re-execute and re-execute. With a spreadsheet, you just have a cell that you put the number in, and it just updates your results for you. So we will be doing that, but it will also be sprinkling Python here and there. I know many of you are, Python gurus. Some of you are just kind of enjoying Python. So we will learn as we go, okay? We will learn as we go. I'll try to bring Python as much as I can. There will certainly be Python when we have bigger, larger data sets. And one of the funnest experiments we will do here in class, like I said last time, we will demonstrate what's called the central limit theorem. That's like why everything tends to be a normal distribution. So we will run experiments in Python and look and observe the data and demonstrate that the theorem is true. All right, and I gave you the action items last time, so I hope you figured out where my office is. I didn't see anyone come say hi to me in my office. I was a little sad that day. But that's okay. Maybe next week you'll come and say hello. I want to introduce you to one of your TAs, Mr. Ashton Phelps. There he is. Okay. Yes. So. Yeah. So you know him. He knows you. That's great. Okay, and feel free to confide in Ashton if there are things you want to pass on anonymously, feedback to the course, etc. But Ashton, as he's working with you, I have certain strict rules on how we run the help sessions. We haven't figured out the help sessions yet because of the conflict with the times for them, because of the conflict with the previous class. But I moved my office hours to 10 to 12 on Thursdays. So hopefully, that's good enough for you. And again, if not, just shoot me a message and we can do a Zoom meeting anytime that works for you. But I will give Ashton certain rules and instructions on kind of how to run things. So don't be mad at him. Be mad at me, okay? If he tells you, look, I can't, I can't do this right now, he's going to tell you, Professor Saad told me to do so. So it's me. It's not him talking. He's just doing his job, okay? With that being said, it's the second TA we haven't identified yet, but I promise you, he's not imaginary. I think I know who the guy is, and we'll have him next week. Okay. Well, we are done with boring stuff, but there will be some more boring stuff too, because I know you guys know a lot, but I have to do my due diligence and pass on the information to you by starting with some, easy-going stuff. It's not that very hard. Some definitions and some things we just need to say that we know. We've heard of these words. It's probably the 10th time you've heard of them, or maybe the first time, but that's okay. Hopefully there's some wisdom also that's sprinkled around in these slides. I really like this quote by Charles, this Whelan guy. He wrote the book called Naked Statistics. It's a really cool book to read. Gives you insights about how people could lie with stats and do fun things with stats. It says, it's easy to lie with statistics, but without them you cannot tell the truth, or it's hard to tell the truth without them. That's so true. That is so true. So the stats is there, the way you present the stats and spin the story. You can tell things in different ways. So that's why it's very important for you to know what people are talking about. Like we also talked last time, it's a good BS detector. All right, I like to do learning objectives for these for my courses, at least the undergraduate ones, just to at least help you plan as you study for the exams and as you navigate the course. So at the end of this chapter, hopefully, I'm gonna read this. I hate reading from slides, but it's a lot of bullet points. So hard for me to memorize those. So we'll hopefully by the end, the goal is by the end of this chapter, you'll explain what is a statistical investigation. So you're doing a study, whether an observation or an experiment. Define a few terms like population, sample, other statistical term. Define the difference between statistic and a parameter. Explain the differences between descriptive and inferential statistics. So that is going to be the biggest piece in this course, because we're going to do both. Really these words, parameter, statistics, sample, etc., they're going to come in really handy later once we start doing some serious mathematics. Explain a few types of sampling methods, how you sample from a population to start doing statistics on things. Explain the two types of statistical studies, observational, experimental. We're never really going to do any studies here, but oftentimes you'll get some. This is for your own benefit. When you read a study, whether they're looking at a treatment, or you're like being hired to inspect if batteries at a certain plant are within the voltage rating, etc. So you'll determine whether it's an observational and experimental study. Define and explain the different types of observational studies. Explain experimental studies, etc., and how to critique a study. Just a few pointers on how to critique a study. Okay, so overview of the course, or more or less of statistics in general. So I told you last time I'm not a statistician, but I am probably a good teacher to teach you statistics, because I had to learn it, as a grown-up, and I was very critical about how I learned it. So I think I can teach it better than if I were a statistician and set in my own ways, right? So there are two types of statistics. Very nice. So there are two types of statistics that you can do. There is what we call descriptive statistics and inferential statistics. Those are the only two types of statistics that you can do with data. Descriptive statistics, as the name implies, it's essentially, they're focused on, you have data, what can you tell me about the data? Think of my radon at home. What was the average radon concentration over the year? What is the standard deviation? We'll explain that better than you've ever heard it, soon. What is the median, etc. Some information about the data. Make a plot about it. Look at how it's distributed. That's all descriptive. But that's it. You stop there. There's the information we collected. And we're not making any predictions about anything. It's like you want to set your budget for next year, right? Your food budget. You look at how much you spend on dining out last year, right? And you get an average and you say, okay, every month I'm gonna save, I don't know, every week I'm gonna put in $20 for dining out because that's been on average what I'm spending, et cetera, right? So descriptive statistics, very straightforward, and that will be the first part of the course, just the first few lectures. And most early on, it's going to be a little boring because, you know how to do a plot. We'll show you how to do a histogram plot. We'll define mean and slash average. We'll define the median. We'll talk about a few extra things as well. Those will come in handy later, but it's really fairly easy. The harder part is when we go to inferential statistics. So, and that's going to be the vast majority of this course. So about 6 lectures on descriptive statistics and 12, 14 lectures on statistical inference. So if I say inferential statistics or statistical inference, it's the same thing, okay? Now, inferential statistics, they are based on making inferences, which means you have data and you're going to infer something to make a prediction. And the idea is we're going to take some data from a sample, which we will define later, but I know intuitively you understand what a sample is. It's just a small representation of the truth, or what we call the population. So for example, the population of students in engineering, I can sample you guys to make a prediction about the population of engineering students, about their habits. Let's say how much they're going to average in their exams, or their coding skills, for example. I can take you as a sample and see if I can make a decent prediction about the population of all engineering students. Now, we will learn that it's just easier to deal with a sample because it's very hard to look at the information about the entire population of engineering students, 2,000-3,000 students, right? Same thing applies for all the population of people who have heart disease, right? You're not going to be able to track every heart disease patient in the entire world. So you pick a sample and then draw conclusions on the population from the sample. Now, what is key here, and that always baffled the heck out of me, because who loves probability here? Good. Oh, okay. Couple. The others, you hate probability, right? Yes. I cannot count. You'll see once we hit probability, I get so nervous about it because it's all about counting. You need to know what the sample space is and kind of what your experiment is doing. But it's all about counting, but oh, good grief, I'm so bad at counting. And it's so hard. And then I read oh crap, statistical inference incorporates probability and uncertainty. They go hand in hand to make predictions, and I was terrified. But there's a way out of this. But still, why do I need the probability to make an inference about the population? I have data here. Can't I just say, well, the average student here scores, or we pick a sample from engineering population, they scored 80% proficiency on coding. Doesn't that mean that the population probably has 80% coding proficiency? I don't know, okay? So that's where probability comes in. Turns out that's not true. You have to make some other things that incorporate probability. I'll give you an example now. So, all right, so here's one example for talking about probability and uncertainty. A pharmaceutical company conducts a clinical trial on 200 patients, so that's your sample, to test a new drug for lowering blood pressure. Using inferential statistics, they analyze the sample data to determine whether the drug is more effective than the current medication. Through what's called hypothesis testing, they conclude that with 95% confidence that the drug significantly lowers blood pressure in the population. So they took only 200 patients and they applied that to 300 million people, or whatever, 1.8 billion people in the world, right? That's insane that you can do that. It's literally a miracle that you can do that. Now, the analysis includes calculating the p-value. We will learn about all of that. But still, my key point, the thing that bothers me so much is, why does inferential statistics require probability? Why do you think that's the case? I can have an answer. Yeah.
So say if you were to like, the world has a lot of chance, and because you are trying to extrapolate, you have to factor in the chance and the noise of your data,
Okay.
no matter what you're doing.
Okay. Any other thoughts? Why would I need, why does probability come? So take the example again of the 80% coding proficiency. Why do I need probability to make a prediction about the entire population? Go ahead.
This is taking into account outside factors
That may influence the decision. Okay. Can you guys put your names in? So what was your name?
Jesse.
Jesse, okay. So confounding factors, right? Things that you have no control over. Probability is going to assess the chance of that. Okay, what else? Yes? It's just, yeah, the result you observe. Yes, okay. Random chance. Okay. Correct on all counts. I hold you correct on all counts. What's your name? Samantha, thank you. Okay. So remember my example with the radon, and we had prior to mitigation and post mitigation. Remember the data? And all of you said, well, it did drop, and I agreed, but then I had that, Marshall with the whip, not good enough, right? I don't know if you remember that show, but anyway, so here's a step back to try to put probability in context, and I give you a very concrete example, and it will fix the idea in your mind. So think of processes in life in general, natural laws, as there is a natural law, a natural process that governs something. For example, how a gas burns, right, or how plastic melts, things like that, how leaves move when the wind is blowing. And then there's observations, outcomes, data that are observed from that physical law. Now, one way to think of this is that probability fits in here, because in probability, when you are applying probability, you have knowledge of the law itself. So for example, I have a fair die. I start with a fair die, or I have a fair coin, and using probability, I can tell that I have 50-50 chance of getting heads or tails, right? So that helps me make a prediction on the outcome. And in fact, you can cast all physical laws in terms of a probabilistic framework, okay? That's what quantum mechanics does. Now, on the other hand, in most cases, we do not know the physical law. We have a hypothesis about it, right? So when Galileo discovered, started observing how things fall and set the things in motion for gravity, he only had observations. He was dropping balls from that tower, and he was observing acceleration, etc. And then Newton came in and sealed that. So what they did, they started from observations. They made a hypothesis about what the law is going to be, right? And that is a form of inference, okay? So statistical inference, we start with data. You observe things. Now, given the data, what can you infer about the law or your hypothesis? So I'll give the coin as an example again, because it's a very easy example. You have a coin, you flip it. Okay, you keep flipping it 1,000 times, and you observe how many heads and how many tails. And let's say you got, what do I have here? 48 out of 100 coin flips, you had heads. So the chance of getting heads was 48%. And you're assessing whether the coin is fair or not. Okay, so that's your physical law. Initially, we started here. I have a fair coin. What is the probability of making certain observations? Next, we started with observations. What can we say about the fairness of the coin? Okay? So think of probability as starting with a recipe for baking cookies. That's the law. That's your recipe. and predicting the likely outcomes that the cookie is going to have certain characteristics. There's going to be a strong strawberry flavor, and then your kids put mustard in it while you were turning away, and then you're surprised with a weird mustard flavor, etc. Versus statistics, what it does, you eat a cookie, and if you are a connoisseur with food, you have a good, taste buds in your mouth, you can tell, I can sense some mint over here, and like be fans of like those wine connoisseurs, it's dry or whatever. The best wine is the wine you like, right? Even if it's $5. Now, speaking of cookies, who likes cookies? Okay, let me see. If you don't like cookies, can you stop? I'm just joking. If you like cookies, I have some cookies for you actually. All right. So come on up, have some cookies. We're gonna occupy here. Okay. Now all you cookie monsters, you had your fix. Now see, that's gonna increase the blood sugar. You're gonna be activated again. So good activation. All right. So I want to come back to this problem. This is a true story. I'm not like as I was planning the course last year when I started teaching it, like why I don't understand. And you go to read a textbook, because the probability would assess this and that, and it didn't make sense to me. But the fact is that you cannot do inference without probability. Now I'll give you the answer, and then I'll give you an example, and hopefully that will be a eureka moment for you. So a formal answer is that what your colleagues have said, but just framed in a different way, is that you need probability to assess whether your data or what you observed just happened by pure chance. Because we are not sampling the entire population, there are so many co-founding factors involved in this. You're just taking a sample. Okay. Now, is the result of my radon treatment just by pure chance? And I mentioned that a little bit on Tuesday, right? So is your result, what you observe, is it just by pure chance or not? And only probability can assess that. So let's do an example. I will take a coin, and I'm going to flip it 1,000 times, and we observe 600 heads and 400 tails, and we want to determine whether the coin is fair. Now, 600 out of 1,000, it doesn't sound much. It could be just like, yeah, if 1,000 times is not that many flips of a coin, maybe we need 1,000,000 flips to really truly tell if the coin is fair or not. But all we have is 1,000 flips. Okay, and this is kind of what it looks like: 600 heads and 400 tails. Now we do expect that for a fair coin, and we will learn later the true meaning of the expected value is in the limit of flipping the coin infinitely many times. Only in that limit do we get exactly 50 heads, 50 tails, in that limit. But if you're doing a finite number of experiments, like 100 or 1,000 or 5,000, even 10,000, right, you're likely to see some variation due to just random chance. Okay, you go and flip a coin 10 times, you're probably going to get 7 heads and 3 tails, but you flip it 100 times, that number is going to get closer and closer to 50-50. So the question is, 1,000, is that a lot? Is that a little? What should we expect the coin to do in that case? So, with 1,000, you could run, there's online coin flipping things. You could get numbers like this. And those are kind of reasonable, right, from just kind of flipping randomly a coin. But 600 versus from 1,000, it's 100 more than we expected, right? This seems unusual, or maybe not. I don't know. Okay, we want to make an inference. Now we ask ourselves, okay, could this happen by random chance if the coin is fair? So we're going to flip the question. We're going to assume that the coin is fair and ask, if we have a fair coin, what is the probability of getting 600 heads in 1,000 experiments, in 1,000 flips? Okay, so there you go. That's where the probability comes in. Using probability, we can calculate this likelihood, and it turns out to be 4.63 times 10 to the minus 11. That's an incredible incredibly small number. Probabilities go from 0 to 1. There's a very little chance that this result could be from a fair coin. And therefore, we will conclude that the coin is not fair. So either way, we determine the loss of the coin. We assume that the coin is fair. We calculate the probability. With a fair coin, what's the likelihood of getting 600 heads out of 1,000 experiments? And that's where the probability comes in. Okay, now, we will learn later, and you've probably taken this, I don't know, or you probably heard it in studies. This is called the p-value, what they call the p-value. The probability value that if your hypothesis is true, that your observation, what you observe is correct. Okay? Now, since the probability is extremely low, we can infer that the coin is unlikely to be fair, and we will define our confidence interval or our confidence in this result. Now, what did I use here to calculate this probability? I told you I'm horrible with probabilities, but thankfully with statistics, and especially with the central limit theorem, there are only like 3 distributions that you need to know: normal distribution and like a gamma distribution, and you're done. Okay, so you don't have to worry about computing probabilities manually like you would in difficult probability problems. In this case, for the coin, the probability distribution, which we will also learn later, is called the binomial distribution. And it just comes with, it's a formula where you plug in how many experiments, how many heads do I expect, what is the probability of getting this and that, and then you get a number. The most critical piece of statistical inference is figuring out what probability distribution to use. Once you figure that out, the rest of the calculations are rather straightforward. Okay? And again, we will see that in future you will see that, unless you've had some courses in statistics previously. Okay, we'll do some definitions now. I know, but we have to do some definitions. Okay. So my name is Tony. I like Tony Stark a lot. It's like a great name. So, okay, some definitions. Again, this is going to be just going through definitions. Population, what's a population? It's all the things, all the people, all the subjects that you're trying to apply the statistics on or do statistical inference. Yes?
For your radon example, would the population include the time in the future?
Yes, the population would be radon concentrations from here until forever, okay. Right? But I only have a sample, a 1-year sample. Yeah. But thankfully, the data is likely to be cyclical because radon is highly my slab is fixed. I have the same carpet there. I have the same cracks. I'm assuming no new cracks are forming, or the time scale for those cracks is a decade or more. Weather is rather cyclical, so I would expect the patterns to repeat themselves every couple of years, right? So if that's the case, then it's probably not really forever. The population is all the radon, through forever. It's maybe over a 4-year period, right? That's my population. So if you wanted to get all the radon data for the population of radon, as you say, maybe a 4-year measurement would give me all the data I need. Yeah, great question. Thank you. So statistics is exciting and attractive and pretty when you're dealing with human subjects, right? Because it affects all of us. We are all concerned about our health, about our well-being, about our fitness, about the food we eat, etc., right? So any statistics that involves humans as the subjects and as the population, we're interested in it. And we're going to understand it. But as engineers, your population is not going to be necessarily people. It's going to be things that you produce. Like my friend, my colleague, he works at US Gypsum. And he designs drywall, like, the walls we have in all your homes. And, his population is all the drywalls that are produced by US Gypsum, okay, forever, from now until forever. Or after they introduce a new process to produce, drywalls, they make, 100,000 a month or so. But he's not going to test 100,000. He's going to sample maybe 5 drywalls or 100 or 15. Right? So the population would be all the things that you are testing. You're making batteries. Your population is all the batteries that you're producing and shipping out. but then your sample would be a small subset of that. Parameter is a numerical description measuring the variable of interest in a population. Okay, so when I say the mean value of thickness in the drywalls that my friend works through, the average value of all the drywalls, that's called a parameter. Okay? And that's called a parameter. And we will assign different symbols for things that are related, that are parameters and that are non-parameters. Because the sample will also have an average value, but the average value of the sample is not necessarily the same as the average value, for example, of the population. The mean height of the students in this sample is not the same as the mean height of the students of all the engineering students. Okay? And they will be assigned different symbols. A sample is a representative subset of the population because it's impossible to measure everything about the population. Now, so population sample, the corresponding thing of parameter to a sample is called a statistic. It's a numerical description measuring the same thing you would measure for the population, but in the sample. So the average of a sample, average height in the sample, average thickness, average temperature, whatever, or the standard deviation or the median, whatever property you're measuring on the sample, that's called a statistic. Okay? It has a corresponding value in the population. It's going to be different, a different value. But for the population, that's a parameter. So the standard deviation of the population is a population parameter. The standard deviation of a sample is a statistic. Okay? Variable, it's a value or a characteristic that changes for each member of the population, height or thickness of the drywall, or temperature or rated voltage for the batteries you're working with, or tensile strength of the material you're producing. Data, that's the data we work with. It's whatever information you have about things. And then finally, census is essentially when you do a study, when you analyze the data from an entire population. Okay, from an entire population, that would be called the census. Let's do some examples. Again, this is easy. Yes?
So what's the difference between a variable and parameter?
A variable is something that varies from one member to another, like height. A parameter would be what's the average. It's a property of the entire population. Properties are not individual heights. A property would be what is the standard deviation in heights in the population, what is the average height of the population. Good question. But a variable is something is related to that parameter, but it will change from one individual to another. Okay? Age, height, having hair or not having hair, etc. Right? Okay. I used to have a lot of hair, by the way. Yes?
So I see that variable is related to the population. Is it also related to the sample?
Yes. But typically, we want to track the variable in the population, but we're only going to apply it in the sample setting. Yeah. Did you have a question? Same question? Oh, he does not have a question. Okay. So a consumer advocacy group wants to survey residents in the Midwest regarding hospital care. And you'll see a lot of these examples are kind of human focused. I think they're easier to understand and relate to because we've all had probably terrible hospital care at one point or another, or great hospital care. The group mails out 11,450 surveys to randomly selected households in the Midwest, and a total of 942 surveys are completed and returned. Out of this group, 57% say that their hospital care was above average. And after analyzing all the surveys, the consumer advocacy group determines that approximately 60% of people in the Midwest are satisfied with their hospital care. Okay? So notice here what they measured in the sample, that the average rating, people saying good, is 57%. But for the end up being a different number, that's what we will learn to do later, to go from that 57% to the 60%. But here the question is, okay, what's the population? Or is it the 11,450 or
The Midwest.
all residents in the Midwest? Okay, all of them, every one of them. Okay, the sample What is our sample?
Would sample be the 942?
Yes, that's what was returned to us. So although we mailed 11,450, we only received 942. So essentially, we've only sampled 942. You know, there are issues with this. What if the 942, only those who are angry with the hospital care responded, right? Because typically it's like when you're either incredibly happy or like very, very angry, you're more likely to answer, right? So out of 11,450, only 940, it makes me a little bit kind of nervous about this. What is the parameter we're trying to measure? Pardon me, satisfaction in hospital. Yes, thank you. And what is our statistic? So, yeah, what is our statistic? So, in terms of numbers, Abby, what is the number for our satisfaction? What is the parameter? Yeah, is it 57 or 60? So, parameter is related to the population. No, parameter is related to the population. So, the parameter, our variable is the satisfaction with hospital care. But the measure of that, the parameter that measures that satisfaction for the population is called the parameter. That's going to be 60%, right? That's what they predicted. And therefore, the statistic corresponding to satisfaction is going to be 57%. Okay? All right, let's do another one. In a survey, 257 residential college students at the University of Utah were asked if they had eaten lunch in the Union. 72% of the students surveyed said yes. After analyzing the results, it was determined that approximately 70% of residential students have eaten lunch in the Union. Okay, so what's the population? All residential college students, okay? Everyone, okay. What is our sample? The 257 students who responded. Okay, so we can ask the variable. The variable is whether they've eaten lunch or not, right? But then what is the parameter that measures that? There's two numbers here, 72 or 70. Remember parameter corresponds to the population, right? So it will be 70. And then the statistic, which corresponds to the number that comes from the sample, it's 72%. So they will be different. Always, they will be different. Unless your sample is very, very large, okay? As your sample size approaches the population size, then the statistic is more likely to be similar to the parameter. Okay? Let's do one more example, and I'll skip the remaining two. Okay, so those are the answers here. After an airplane security scare in 2011, a phone survey company interviewed 679 American air travelers about increased security measures at airports. Okay? The report stated that 82% of American air travelers are in favor of United States passports using full body scan imaging on airline passengers. Okay, so what's our population? All American travelers, all of them. Okay? What is our sample? The 679. Now, we are given one number. Okay? 82%, the report stated that they concluded that overall 82% of American travelers are in support of the new measures. Is that a parameter or a statistic? Oh, we got a split. All right, who says parameter? About, let's say what? 70% of the, much more. Okay, who says it's a statistic? Okay, why do you think it's a statistic?
They haven't done the work that they need to do for a population level parameter.
But the report, we're hiding the story from you.
From the report, so it's not saying that that's what the survey, the people from the survey said. They're saying of the whole population.
Of the whole population, yeah. Yeah, so there might be lack of clarity in the words, and you will see that in a lot of studies, and that's what will make you ask questions. Hey, wait, is this number related to the sample or the population? But as best as you can tell, they're making a claim. Okay, after we did our analysis, we conclude that 82% of American travelers are satisfied. So that is going to be the parameter. Okay, that's going to be a prediction on the parameter. Okay. Here's another example. Should we do it? No, let's do it. Another independent survey company also conducted a survey in response to the same incident of the airport scare. The National Telephone Survey of 1,092 adult Americans found that 62% of Americans surveyed favor racial profiling as a means of determining which passengers to search at airport security checkpoints. Okay, so what's the population? What's the population? Adult Americans, not air travelers, but more. This is a larger group, right? It's all because they just called people whether they travel or not. It's hard to find someone who's never traveled, but they're still okay. And now, what is our sample? 1,092. Now, this 62%, is it a parameter or statistic? Statistic, yes, because it's clear in saying 62% of Americans surveyed favor the racial profiling thing, etc. So they're specifying that this is a number from the sample, so it is going to be a statistic. Okay, you will find many studies that don't mention either way, and so that's going to give you fuel to say, well, this no, I need to understand this better, so I can make a better decision, etc. Okay. Again, this is a different picture for how we're going to use statistical inference. We're going to take information from a sample and specifically certain statistics from a sample, like average, standard deviation, etc., and make a prediction about the population. So my friend will go and measure a batch of 10 drywalls, and he will take the average thickness of the drywall, and measure the thicknesses of the drywall. He'll compute the average, the standard deviation. He'll measure certain thermal properties, and then run a statistical analysis to make a prediction about the population of all the drywalls that are coming out of the company. So the company can come out and say, well, our thickness is this with plus or minus that. It's what, 2 inches or 3 inches plus or minus 5%, and so on and so forth. Okay. Now, in a descriptive statistics, like we said, we're just summarizing data from a sample or a population. If you did a census, you can totally summarize the data from the census, and that's still called a descriptive statistic. You don't need inference anymore. But anything that you take data from a sample and make a prediction on a population, that's called an inferential statistic. So here's an example. A consumer advocacy group wants to survey residents. Oh, that's the same example. Of the Midwest. I should have read the slides before coming here. The group mails out 11,450 surveys. Again, total 942 surveys are completed and returned, okay, et cetera, et cetera. Determine which is descriptive statistics and which is inferential. So the descriptive statistic is that this 57%, right, that we are describing what we have observed in the sample. And then we make an inference that 57% mathematically becomes 60% when we incorporate probability. Okay, let's resume. So next we will cover again we're never going to touch this in practice once we do the actual statistical calculations, but if you get more involved in doing studies and experiments later, those will come in handy to have at least seen them, or when you're critiquing a study, you can at least have some guidelines on where to start. I mean, we cannot really cover proper all the what's required. There are people who specialize in doing observational or doing experimental studies, so that's usually a different team. And many times as a statistician, you're only focused on one aspect of things, like the calculation of the likelihood of certain things doing the inference. That's what we're interested in. But still, it's good to know what's out there. So when you are designing a statistical study, we'll see there are 2 types of statistical studies. But you want to understand, okay, what am I trying to answer? What question am I trying to answer in my analysis? Am I trying, like with my radon data, I'm not trying to answer whether there's high pressure or low pressure system outside. I'm trying to answer whether radon actually decreased or not. You install an air conditioner in your, in your shed, for example, because you're gonna do a workshop there, and you're gonna have an atelier there, and you're gonna do some work there. And does it make it cooler or not? Right? You're not. So you have to ask yourself what question you're trying to answer. To be clear too, what is your population? The radon population or the drywall population. What variables are we going to record? Because you don't have to record just one variable. Since you're doing, if you're going and asking people questions to collect data, you might as well collect as much data as you can, because you don't know if one piece of data is going to be a confounding variable for another, like particulate matter in the atmosphere and in schools, etc. Usually a confounding factor for it can be humidity, because when there are water droplets in the air, there's more likelihood for particles to adhere to them. Same for viral transmission, for example. Okay, how during peak COVID season, we wouldn't go to like an indoor sauna or like a heated water pool, right? There's like all sorts of water. The humidity is almost 100% there, and there's much easier transmission rates there. So you might as well measure, identify what variables you want to measure. The two important questions are going to be what sampling methodology you will use. And again, we're not going to be concerned with these, but you need to know what they are. There are a ton of sampling methodologies, not just simply random sampling from a population. There are different ways to sample, because many questions you're trying to answer could have bias if you just do random sampling, so you need to do it correctly. And whether you're doing an observational study or an experiment, which is kind of clear, but we will define as well. Next, you collect the data, organize the data, and analyze it to answer your question. Obviously, eventually, we will be here. We will be at this point in this course. We're going to assume the study was done, the data was collected, the data was organized. You're given the data. Give me an answer. Okay, make a prediction. So let's imagine we want to analyze an example, understand the significance of walking to reduce heart attacks. Okay, the goal of the study is to determine if walking 30 minutes per day will reduce the occurrence of heart attacks. So what question are we trying to answer? It's kind of obvious. Does walking 30 minutes a day reduce heart attacks, right? Okay, what is our population? Yes? Everyone?
People who can walk.
Sure. Or people who are at higher risk of heart attacks. Because if you are generally healthy, you don't have family history of heart disease, your baseline risk is just minimal, right? So I'm more interested, more likely the population is going to be the people who are at higher risk of heart attack. But it's not wrong to say that for the entire population, because their baseline risk is baseline anyway. It's not going to be reduced by much. What variables would we record?
Whether or not heart attacks occur.
Or also, what other variables will we be recording? So yes, that's an important data point. Whether they and how many minutes they're walking. Yes. So we can try to correlate between minutes walking and if it did reduce heart attacks. Okay. Perfect. Let's do another example. Neurologists want to study the effects of vitamin C. Is like this. What was the story behind this? That vitamin C can prevent colds and whatnot. And I think the story comes from. Does anybody remember the story of the sailors and they were on a boat and they were getting sick, but then they started eating oranges and they got better, and they thought they were just being cured from the cold. It wasn't the cold, there was some illness on the boat. I think that's, pardon me? Yeah, okay, so you know better than that. So anyway, so vitamin C is is still promoted today as, it does feel good though, right? If it's a placebo or not, I don't care, right? If it helps me not get the cold, that's great. And so the goal of studies see if taking an intravenous dose of vitamin C, stick me with vitamin C, will reduce the amount of nerve pain reported by patients. So what question we're trying to answer?
Does vitamin C help with nerve
nerve pain, correct? And what's our population? Yes, those who have nerve pain. And what variables what will we be recording? If they took the vitamin C, what dose they took and whether nerve pain improved or not, right? Now there are many issues in these studies because this could be highly subjective, like the measure and and if they are responding, if a nurse is present there and the nurse tells them, oh, what's your pain level today? And I was like, what's your pain level today? Or like the nurse's interpretation of 1 to 10, what it means, right? So you could screw up these studies in all sorts of ways, right? But that's why you need to repeat these experiments on different samples and try to reproduce those results over and over again. It's an amazing tool, statistics, but also these studies can be really fraught with a lot of errors. Thankfully, in engineering, we don't have nearly as much as this kind of bias of subjectivity. You measure voltage on a battery, right? And you're not asking the battery, how do you feel about your voltage today, battery, right? So there are two types of observational studies, observational experimental. As the name designates, in an observational study, you're only measuring existing data, things that are already being done. You're not running and you're not actually applying a treatment to test something before and after. Like with my radon data, prior to the mitigation, it was an observational study. I only observed radon in my basement. But then when I applied the radon mitigation, that's an experiment, a sort of an experiment. I'm trying to test if this radon mitigation system does actually reduce radon. Okay, so an experiment requires you that you actively intervene in the process and apply a treatment. So we will hear this word treatment. Essentially, you're applying a fix of some sort to see if it changes the outcome of certain things. Could be a drug, could be a certain chemical coating you put on your material. There are pros and cons and different properties of observational studies and experiments. So in terms of intervention in an observational study, there's no intervention. You're just observing data. So you're just collecting data. There's no overhead. You're just asking, give us your data anonymously, and we'll just do our thing, whatever with the data that we have. An experiment, you're actually applying, you're actually making a treatment, you're actually making conscious choices, and you have to do those carefully so that your study is meaningful. For an observational study, the purpose is just identify correlations and make, you could still make an inference totally from an observational study and see if, for example, let's say I want to see if vitamin C truly affects nerve pain. And it just so happens that hospitals serve oranges every day, at the U of U or the California hospital or whatever, Florida oranges, right? So they serve oranges every day. So people there consume vitamin C just by being at the hospital. So we could observe patients who go to neurologists or are at the neurology doing neurological surgery and whatnot, and see what they do. So, but with the experiment, you're trying consciously to establish cause and effect, right? So when I put the medication system, I am intentionally wanting to observe an effect on radon systems. In terms of control over variables, in observational studies, you have no control. You're given the data that's there. You can't go back in time and run things. It's like whatever is available, give it to me. But in an experiment, you have high control because you're designing, you're planning. You say, I want you to administer, 30 milliliters of vitamin C, or like do this much of chemical coating, and you're planning every question, every step of the experiment. In observational studies in general, you cannot determine cause and effect because the data might be contaminated. You might not have all the data you can. But in an experiment, you can determine cause and effect because you apply the treatment, you see an effect, you take the treatment out, you see it bounce back, then you start having high confidence in saying whether you have causality there. Some examples: smoking and lung cancer. this is an observational thing, right? It's highly unethical to tell people, to have people on purpose smoke, right? Come, we're going to give you a bunch of cigarettes, right? It's, as a former smoker myself, I'm like, please don't offer me cigarettes. But that's an observational thing, right? You can do. It's an observation. You just measure the effect. You just collect data. There's this very strong correlation and causative effect between smoking. I mean, it's correlative, but we know it's causative as well because we can now analyze the pathology of cancerous lungs and see how carcinogenic these particles are, etc. So we can establish causality here. Although this says you cannot establish causality, we can in many cases. With an experiment, you can measure whether a new drug is effective or not. And in terms of negatives, in an observational study, you might not have good quality data, or you might have good quality data. The experiment is as good as your experimental design is. And sometimes with an experiment, you are limited. So right now we are running huge experiment across all elementary schools and up to middle schools in Utah, across the entire state. And we are installing radon monitors, we are installing particulate matter sensors. It's a huge study. There's over $500,000 worth of sensors being installed across the entire state. And we're collecting data. But it never goes as we plan, because the IT guy at school A was like, nope, I'm not allowing you to connect to the internet. And so we cannot gather certain types of data over there because we do not have connection to weather data outside. So we have to either discard that school or not measure everything at that school. In another location, you cannot install the sensor here because we don't want it to look ugly and whatever. And so, there's all sorts of constraints that come in the way. But if you can control things in a study, I mean, the best study you could do is like where you own the building, right? And you can do whatever you want, like what I did with the radon in my house. But still, I didn't want them to install the mitigation system in the middle of my basement. So, there you go. Okay, so we'll do one example. Which type of study would you conduct in the following? So you want to determine the average age of college students across the nation. That's an observation. You just ask the question. Researchers wish to determine if the COVID vaccine will help prevent severe disease of COVID-19. Experiment. Yeah, it's better done as an experiment. Now, you can make an observation in that if people are refusing to actively take the vaccine, and you just collect data from other locations where people who got vaccinated actually did improve. And it will be harder to establish causality, but it can be done. All right, sampling methods. Before we go, still have 10 minutes. There are a few ways to collect samples for a population, and this is definitely not comprehensive. And again, this is not going to be part of our analysis because we are focused on that last step in making inference. Given the data, so the study has been done, whether an experiment or an observational study, so we're not concerned with that. You're given the data, make a prediction, make an inference. Does the hypothesis or whatever we would after, is it true or not? But you still need to know kind of what kind of sample, so you sound, that you know what you're talking about. There's a few different sampling methods: random, stratified, cluster sampling, systematic, convenience sampling. We'll talk about these few. The simplest method of sampling and the most straightforward is called random sampling. You essentially just randomly pick people from the population. So what they typically do, they assign a number to households in a state or in the college, whatever, and then just do a random number generator, and they pick randomly, and then they can contact the persons, and that's it. You're sampling randomly, okay? Now, whether the person responds or not, that could lead to bias, etc. The second type of sampling is called stratified sampling. I like these animations. I was working on them, took a few hours, but I figured them out. Tell me what you think about them. So if this were the population, So you see they have different characteristics, you know, could be, I don't know, could be gender, ethnicity, could be hair, whether they have hair or not, could be all sorts of things, right? Could be, you know, they have genetic predisposition to this or that. There are different, you know, there are differences between all people in a population. In stratified sampling, depending on what you're trying to measure, you try to stratify or separate the population into groups that could influence your results, okay? So what you would do, you would create stratas of these people, of the population. You say, okay, the first stratum is people who are blue, the second stratum, people who are red, third, people who are green, fourth, people who are orange, green, red, etc. It means, okay, people who have this, let's say you're looking at risk of you know, certain cancer, pancreatic cancer, and try to determine if a certain gene mutation does that. Then you stratify the people. You have 4 gene mutations that you're concerned about. You're going to stratify the people by that mutation. The blue people have the mutation A, red people mutation red, etc. Right? And then you randomly select from each stratum generally the same number of people, so you're consistent, but you apply random sampling from each stratum, okay? From each stratum, and you select those people. A cool animation, right? You select those people, and that would be your sample. So that's called stratified sampling. It comes from the word strata. It's like layers, okay? Layers. Yeah, I have a formal definition here for you if you want. Cluster sampling is the next type of sampling. Again, your population is mixed up like this. And then what you do, you create different clusters that represent the population. So for example, those could be classrooms in a college, right? So each classroom is a cluster representation of the college because, you know, you go to an average classroom in engineering, it's going to look the same, about 50 students, about the same, you know, age, etc. They're going to look the same, right? And so you separate them into clusters, and then you randomly select clusters. Okay, so if I were doing an analysis on GPA or coding proficiency, I would just simply randomly select classes across, you know, freshman engineering. Okay, just randomly select classes. That gives me automatically cluster sampling. I have a definition for that. Systematic sampling is you select every nth person in the population. Okay, so here I'm selecting every third person in the population, and you just select them just like that. So it could be, you know, in exit polls, for example, you could select every third person coming out, or like you line people up, and you're just like, okay, I'm just going to systematically sample the third person, right? Just again trying to increase randomness and all of this. Finally, convenience sampling is if it's really convenient for the researcher, right? It's really convenient for me, for example, right now to get your average scores because I have access to that in Canvas, and you don't have any score right now, but like, you know, by the end of the semester, I can get your average score, and I can just, I can say this is my sample, right? It's convenient, it's easy for me, but it's not always the best, okay? It's not always the best, but it's still a type of sample. So knowing what type of sample allows you to criticize a study and say whether a different type of sample would have been better. We'll do a couple examples. We need to identify what type of sampling this is, and so we start. A pollster surveys 50 people in each of a senator's 12 voting precincts. Okay, so you might think that the voting precincts are the clusters, but they're not, because different precincts could contain different populations, right? So this is more like a stratified sampling, okay? Because the population inhabiting, you know, Cottonwood are more likely to be, you know, people who like to climb mountains, who love nature and Gaia. People living in Salt Lake, they want more focus on public transport, etc., right? So they're not really, they're different populations, but they are separated by, you know, the living conditions they live in. So it's stratified sampling in this case. Quality control department at a cereal manufacturer measures the weight of every 10th box of the assembly line. Systematic sampling. I'm answering this for you because I don't have the definitions here for you to remember. So that's called systematic sampling. And finally, a female student walks down the halls asking students how much money they would spend in a food court. That's convenience sampling. It's just convenient for her to do that, right? Okay. There's some other examples here. I'll let you summarize those, and I'll let you review those. I mean, again, this is it. In homework 1, you'll have a simple question like that. So, but I'm not done with the slides though. But this is it for kind of for the sampling. So next, we're gonna look at types of observational studies. So remember, you're not spying; you're only observing. You're merely observing. So you're not interfering with the data because the data already existed. Okay. There are different types of observational studies. Remember, because the data is already there for you. All you're doing is taking all of that data and doing an analysis on it. There are a few types, and you've heard they tell you, oh, a cross-sectional study report. Hello? Reported this or that, or a longitudinal study was applied to people who have heart disease. A meta-analysis tells us this and that, or a special case study. Oh, thank you. Thank you. Okay, so a cross-sectional study, simply data are collected at a single point in time. So you're taking a cross-section of time. Okay, you collect the data, or you have data across years, but you say, I'm going to take one snapshot, one month or 1 year. That's a cross-section. You're taking a cross-section of the data. A longitudinal study, you follow a particular group of people over a period of time. So how are people faring with a certain drug, or how are our drywalls, throughout the years, how are they holding up? Over 10 years, etc. That's a longitudinal study. A meta-analysis is you compile a summary of other studies. So there's a lot of other studies that are being done. They could be longitudinal, cross-sectional, etc., etc. You compile all of them. That's called a meta-analysis, a meta-study. And finally, a case study, it looks at multiple variables that affect a single event. That seems like a very kind of vague discussion, but vague definition. But a case study, you're like looking at one specific thing, like your drywall, for example, and what variables affected. Yes, Savan?
Is that more like following like a certain these people, or is it more like looking at 12-year-olds like every single year?
No, it needs to be to follow the same people. Yes, the same, yes. I got the, so what your colleague is asking, are you following the same unique group of people throughout the years, or you're looking at one group of people, like 12-year-olds, over many years? No, you need to follow the same unique group of people because you want to see the long-term effects of a certain treatment. Okay, good question. Okay, so a group of 220 patients followed for 15 years, that's longitudinal study, right? You can tell, yeah, we followed patients for 15 years, longitudinal. Gastroenterologist surveys 130 of his patients 6 months after gastric bypass surgery. What is that? Cross-sectional, right, at one snapshot in time, 6 months, okay? I have a couple other examples here, and I can let you go now. Thank you so much for your attention. Great first week. Let's have a great semester. Have a great weekend, and Godspeed.